Thank you very much. So thank you for the invitation to give this talk. So I will talk about, as Alain said, about large deviation principle for microscopic observables in Eviterd matrices. And so this is a joint work with Charles Bordenave and Camille Mal that we just posted last month. So what is it about? So the macroscopic observables will be typically the empirical measure of the eigenvalues of random matrices. And I will also consider the traffic or the non-commutative distribution of these matrices, and they will be, so our results will concern Eviterd matrices, so typically matrices with a lot of zero entries and a few non-zero entries. But before going into this special matrices, let me tell you what is known about the empirical measure of the eigenvalues. Oops. Okay, so I will consider Xn to be n times n a matrix, which is symmetric. So I could also consider Hermitian matrices, but somehow I decided at some point I will only restrict my talks to real entries because usually complex entries are even or the same story, except you have to take more complicated notation. So I will talk about real entries, but it could be complex or whatever. And then so I have n eigenvalues. The eigenvalues, and I want to consider the empirical measure of the eigenvalues. Okay, and we ask if we can prove a large deviation for this, and well, because I understand the audience is mixed, let me remind you what is the large deviation principle. So we say that Ln satisfies a large deviation principle with speed an and good rate function I. So an is going to infinity, as n is going to infinity, if and only if. So here I will see, okay, so for all f closed, so I see Ln as a probability measure on the real line. I have that the lim sup of 1 over an, the log of probability that Ln belongs to f is bounded above by minus the infimum of I over f, and you also have the for O open, the lim inf of the same thing is bounded below by minus the infimum of I over the open set. Okay, so that's the definition of a large deviation principle, and typically it amounts to prove this thing for f, which is a small ball, f and O, which is a, well, so it's a small ball around a probability measure. And so what you see that what this says is that in this case when delta goes to 0, 1 over an of the log of the probability that the distance of Ln to mu is smaller than delta. This is going to be bounded above by minus I of mu. And this is also the same thing as when the limit, when delta goes to 0, of the lim inf. Okay, so this is known as the weak large deviation principle. Okay, so this is what basically we want to understand, is the probability that for any given probability measure mu, can I estimate the probability that my empirical measure is close to this mu? And it turns out that if the lambda I or IID variables with some low p, then it's well known that you have the Sanoff theorem and you have always a large deviation principle with speed n, so an is always equal to n, and the rate function is the relative entropy. Okay. Now what happens for random matrices is much more complicated, and in fact many things can happen. And in fact the rate, as we will see, can depend a lot on the nature of the entries. Okay, so okay, yes, I should have done that before. Okay, so what do we know about these large deviations? So the first result is so if you have a GOE matrix, so X is GOE, then a large deviation principle was established. So with the speed n squared and the rate function I, and I, so this was done by Benarus and myself based on a heuristics from Dan. So what is I? So I is I of mu can be written as some g of mu minus the infimum of g of mu, and g of mu is the integral of x2 plus y2 over 4 minus the log of x minus y d mu x d mu y. Okay, so if you have Gaussian entries, you can prove a large deviation principle, and the proof is not very complicated. The idea that you have this well-known joint law of the eigenvalues, which is very special to these Gaussian entries, and which write that, so if you look at the joint law of the eigenvalues, this is this famous Coulomb gas interaction. Okay, and you can see that this density is approximately a function of the empirical measure. So it's approximately in the sense that here you are adding the diagonal terms and things like this. So it's not exactly the case, but you can think about it like this, and then the large deviation principle is always more or less going to be kind of Laplace method. Okay, you are going to estimate this density on the small ball, and you will find that on the small ball this is approximately around mu. This is approximately exponential minus n squared g of mu. Okay, so this is but I want to emphasize here that it's still open for any sub-Gaussian case. Open for every other sub-Gaussian case. So namely, if you have IID entries above the diagonals, which are sub-Gaussian, we don't know how to prove this large deviation principle. Okay, another result which was very nice and which was due to Caputo and Bordenave is a case of stretch exponential. So what does this mean? It means that the probability that, so your entry, if you multiply by square root of n, So the probability that this is greater than t is going to be like exponential minus a times t alpha, and you have the same thing. So when t is going to plus infinity, and you have the same type of thing when t is going to minus infinity. Okay, and here alpha should be smaller than 2, so it's in 0, 2. Okay, so you are still in the range where if you look at the matrix with entries xij, so these are going to be a centered entry with, I mean, you can take the covariance 1, and then you know that you have convergence towards the semicircle law, and you could expect maybe that the large deviation will be the same if you believe in Senoff's theorem, but this is not the case because what Bordenave and Caputo proved okay, so maybe I should say that my favorite matrix all over would be with independent entries. Okay, so Bordenave and Caputo in maybe 14 prove that so the ln satisfies the large deviation principle, and the speed is 1 plus alpha over 2, and some rate function I. Okay, so you see that the okay. Yeah, okay, so you have a rate which depends on alpha, and in fact you can see why this rate should depend on alpha. Because if you want to create a deviation of the empirical measure, it's, for instance, enough to create a deviation on the entries on the diagonal. And so if you want your matrix to have some entries like some D, which are of order 1 over the diagonal, and you leave the rest to have a classical typical behavior, so what you will see that your matrix look like D plus a Wigner matrix. Okay, so this will imply that Ln should be close to the free convolution of the semicircular law plus the empirical distribution of the diagonal values. And then you can see that the cost to create this will be, so the probability to create this D will be approximately the product of the weight, which will be minus, so A or B. So maybe I could say, well, I could imagine that they are only A and B are equal to simplify. And so this will be A times square root of n times di to the alpha. Okay, so this will be the probability to have this large eigenvalue, and this is like the probabilities of order exponential minus n1 plus alpha over 2. Okay, so of course to prove that an exact estimate to do this deviation is more sophisticated, but in this way you can see that you get a lower bound to create a deviation on the empirical measure. Okay, so you see that you have a localization phenomenon which occur as soon as you have stretch exponential. And a similar phenomenon was proven recently by Fanny Augeri. And what she proved is that, so she considered again sparse entries, but with a sparsity given by a Bernoulli variable that I'm going to describe, and then she also gets a large deviation principle, and the speed depends on the sparsity. Okay, so Augeri. So it's So she considered the case where the xig or big times yig, where the probability that big is 1 is of order p, is p, and this is 1 minus, these are Bernoulli variable. And p is much bigger than log n over n, and much smaller than 1. And you need to renormalize by square root of pn. And so you still have typically semicircular limit laws. And then what she gets is a large deviation principle with a speed which is p times n squared, and some right function that I will not precise. Okay, so you have this kind of family of large deviation principle. So what we considered with Camille and Charles is a case where P is of order 1 over n. Okay, so A Viterl matrices. So what does it mean? It means that, so maybe I should put it a bit. So it means that if I take a subset of R, so which does not contain the origin, then I want that the limit as n goes to infinity of n times the probability that xij is in A. So this goes to some lambda of A. Okay, so this is some Radon measure. So this is what we call A Viterl.
Maybe I missed it. What are the hypotheses on the Y's, the Yij's, in familiar?
I forgot, but I think it can be bounded. The idea is that basically you have some sparsity which is introduced. So this will be 0 with, well, probability 1 minus p. And yeah. So yes. And the y, so you multiply it, so Hadamard product, so the Yij will also be IID. I think you can take them bounded, for instance, and maybe centered, I think, maybe centered, yes. Something like this. Yeah, I think they should be centered. Let's say centered and bounded. But the importance is that introducing this sparsity, you get some large deviation that you can prove, so it's not like sub-Gaussian, because there is this sparsity. The speed is not n squared like in the Gaussian case, but it's p times n squared. So p goes to 0. And she gets the large deviation in this whole range. Okay. Yes. And what we consider is really sparse. So it's in the range where the limit laws are not going to be the semicircle law anymore. It's going to be these Levy matrices or these A Viterl matrices that Zakharevich considered. So in this, in all the previous families, stretch exponential of this family, you still have the limit law, which will be the semicircle, if you renormalize correctly the things. But here it's not the case anymore. Okay, the examples I want to discuss is, so it's an example like Fanny. Okay, so but this time the Big will be 1 with probability d over n. Okay, and the Yig are independent. And if you want, you can take them, yeah, you can take them bounded if you want. Okay, so in this case, it's quite easy to see that, so this will be satisfied, okay, because A should not have the 0 element. This will be satisfied with a lambda of A, which is d times mu of A. So let's say ID log mu. Okay. And the second example we have in mind is the case where we have this alpha stable on trees. Okay, so it means that so the probability that this is greater than t is going to go like p t minus alpha when t goes to plus infinity. And the probability that xig is smaller than minus t is going to go to 0 like q t minus alpha. Okay, and alpha is in between 0 and 2. So we really have a limit law which is not the semicircle law. Okay, and so in this case you can also compute that lambda, so this is working with lambda which is going to be p of t positive plus q of t negative, and then you have alpha t minus 1 dt. Okay, so these are the examples we have in mind, and so the theorem we prove is that if you have a finite mass, then so Ln satisfies a large deviation principle with speed n. So you would expect the n, because here you should take p, which is 1 over n, if you want to continue this family of result, and some rate function. Okay, so that's the first series of results on the empirical measure of the eigenvalue. Is there questions? So then I will, yeah.
I depends on lambda.
Oh, yes. Yes. Okay. You don't have other questions? Yes?
So this includes the agency matrix of another Schlick graph?
Yes. Yes. Okay. So before I go to the idea of the proof, and let me mention, so we call this macroscopic observables because we have this second idea, which is to look at more non-commutative objects. So this is a large deviation principle for traffics. And so it's more non-commutative. So we want to consider now X. We want to consider, let's say, a P independent evitered yes, I realize that above, yeah. Okay, I don't need to have this condition over there in the theorem, but I will correct it when I get the. Yeah, I realize this condition I wrote does not include the alpha stable law, and we can do the alpha stable law. So okay, the two examples I presented we can do. Okay, but I'm not going to get on this blackboard. Okay, so. Imagine that this is independent evitered matrices. Then what is the traffic distribution? So it's kind of generalization of the non-commutative law. So we take H. So it's not, we don't evaluate it at polynomials, but at these connected graphs. Okay, so we have a connected graph. So this will be kind of the colors. This will be the edges, and and V the number of vertices, so it does not depend on the dimension. And what you want to define is, so the traffic of these matrices will be 1 over n as the sum of, let's say, the maps from V into 1n, and the product of UV in E of the entries L of E, and maybe I have also epsilon E, so maybe it's also epsilon. So epsilon it can be the transpose, and then you have phi of U, phi of V. Okay, so somehow it's more general than the non-commutative distribution, which would amount to take cycles. Okay. And then
Phi is any map.
any map from V into no, at this point no. It's only for you have the specialist Camille. It's not an isomorphism at this point because it's not the injective map, so it's any map. Yeah, I don't want to say anything wrong about traffics. Okay, so yeah, so it's any map because you can have several. You can have identification of two vertices going to the same value, things like this. Like when you do the trace, you sum over all indices. Yeah. Okay, so that's. Let me. Whoop. Okay, and so what we wanted to do was a large deviation for this kind of quantity. So you would like to understand what is a kind of probability that this belongs to some traffic. You could imagine to have kind of weak topology for these guys, and you would like to do to do large deviation. So yeah, so large deviation for 2n. So a bit in the spirit of what Daniel Voiculescu proposed. So I remind you that so Voiculescu entropy, so microstates. So in this case, so you can imagine you take P, so GUE matrices, and what you would like to understand is the volumes of the probability that somehow the trace of so this is a p-tuple of matrices. So you take non-commutative, say, monomials. You take a threshold state. Okay, the max over all the monomial of degree smaller than k. Okay, so this is kind of a small ball around tau. And eventually, because the topology of polynomial is not good, you may have the idea to restrict yourself to bounded matrices. Okay, and so the definition of Voiculescu's entropy. So you take first the sum, the limit when n goes to infinity, and then you take the limit as delta goes to 0, and r goes to plus infinity, and k goes to plus infinity. So this is what defines the non-commutative entropy of the threshold state tau. Okay, and so what is very sad about this entropy is that it's not yet a full large deviation principle. So the first question is that can you replace the lim sup by lim_inf. And so the second question is, can you get the rate function? Okay, so rate function. So there is this candidate that Dan defined as the chi star, which is the so-called microstate free entropy, and so it could be proven that there is a bound. So by bien Capitaine on myself, but also the new proofs by Jekyll. Okay, but still it's not an equality, so it's still not clear whether this is the right candidate. And the third question is, can you prove that under freeness the entropy sums up? So namely, if you have the free product, so if you have the joint law of two sets of variables, can you write that this is the sum of the two entropies if the family X and Y, so X, so it's a family X1, XP, and Y, it's a family YM, YP, YN of 3. Okay, so up to my knowledge, this is still open. Okay, and so we just thought we are for the Eviter matrices it's easier, and indeed it is. So we can carry out this program. And let's see. And so what we did was to define an entropy which is similar to the Voiculescu entropy, but for the traffics and for these Eviter matrices. Okay, so j'ai un quart d'heure, c'est ça, un petit quart d'heure. Okay. Okay, so so if I want to give you some idea of how we prove that, let me say quickly what we prove is that we define chi lambda of so this traffic, a traffic which will be the limit as n goes to infinity of 1 over n the log of the probability that so I take my matrices into some set, so it's similar to this cutoff that Voiculescu introduced. And now I take some distance and traffic, so maybe I can take similarly the maximum over all the h with E, which is bounded by k. And then I take the traffic of h minus the limiting traffic. Okay, so this is similar, and I take the limit as so delta goes to 0, k goes to infinity, and theta goes to infinity. And so B and theta, it doesn't bound the spectral radius, but it bounds the number of non-zero elements on each row and column, and also the entries. Okay, so it's kind of the right thing to do for us. It's to bound the degrees, the number of non-zero elements, and the value of the entries on each of them. And so what we prove is that so here, so the theorem is that we can answer all these questions. So we can replace lim_sup by lim_inf. We have some value. some formula, and we have summability under traffic independence. So what is traffic independence? So in free probability, you have variables which are asymptotically free when you conjugate one family by unitaries. In the case of traffic, you have asymptotic traffic freeness if you conjugate by independent permutations, which are following the uniform measure. So this is also true. So you have additional addition under independence. Okay, so that's kind of the theorem. So I realize I don't have so much time to tell you about the proof, but let me say something. I still have 10 minutes or 10 minutes. Okay, so how do we prove that? So that the idea is that, in fact, in the case of these Eviter matrices, you have a very sparse matrix, and you can encode that into a graph. You can associate to your matrix a graph. So if you are given a matrix Xn, so you can associate a graph, let's say G of Xn, which will be a set Vn on some edges and some marks. So it's a marked graph. And so what are the edges? So it's simply the collection of 1 to n. So the edges will simply be the place where the entries are non-zero. Okay, and the mark, so if you have an edge, because the entry is non-zero, then the mark is just the value of the entry. Okay? And the point is that this, so asymptotically, this will be a locally, so this lives in the family of rooted, locally finite graphs, marked graphs. Okay, and in fact, you can prove large deviation principle for these graphs for the Benjamin-Ishram topology, and this is what Bordenave and Caputo did a long time ago. So, okay, so if you assume that the theorem is that, so if you undo this space, or maybe I should be more precise. So now I'm trying to go quickly, but if you consider the neighborhood distribution of your graph, so you define U of G of Xn to be given by 1 over, so if you have a graph, you consider the neighborhood distribution, which is given by the sum over all the vertices of a Dirac math at the equivalence graph of your graph. So you are looking at the neighborhood of your graph up to isomorphism. This is what you're doing with this Benjamin-Ishram topology. And then, so the theorem is that, so if, so this time you have to, is finite, then you have a large deviation principle in the scale n on some right function, sigma of lambda. So this does not cover the case of the alpha stable laws, because in this case the entries are not zero in general. But what you can see that if you look at the number of if you look at the probability that an entry is big, so greater than epsilon, it's going to be like 1 over epsilon alpha to the n. Okay, so the case of alpha stable law. Okay, and then what you can see is that you can, if you change the topology by considering graph by removing all the entries which are greater than epsilon, but letting epsilon going to 0, you have what we call networks, and you can also prove a large deviation principle. Okay, so this is, you need to do large deviation principle for networks. And the last thing that I want to say that okay, I told you about large deviation for the empirical measure of the eigenvalues and traffic, and I'm going to this large deviation principle for graph. So the most important thing is that you can go from one to the other, and this is because if you look at the empirical measure of the eigenvalues or the traffic, they are going to be continuous function of this neighborhood distribution. So maybe I can show you this in the last. Okay, and so if you know that the quantity you are considering are continuous functions, then you can, by contraction principle, deduce the large deviation principle. Okay, so yeah. So maybe I should say here that so there was this work of Bordenave and Caputo, which is really the starting point for all of this. Okay, so the last point is that if you look at so Ln and tau n, you can see that they are continuous function of this neighborhood distribution. And to do that, you can maybe just restrict yourself to this kind of set where everything is bounded. Then it's not difficult to see because, so if you look at Ln of, so if you look at some moment under your empirical measure, what this is going to be, it's going to be 1 over n, the sum of x I1, I2, x ik, I1. Okay, and so you can rewrite this, so it's I1, I2, Ik. And if you look at this, this is just going to be some function of your graph g of xn rooted at I1. Okay, because this is just, because of this assumption, it's just going to be a finite sum of your entries. And by the Benjamin-Ishram topology, this is continuous. You can do exactly the same thing with the traffic. I mean, it was made for that. It's just a sum of continuous function of your graph if you look at it locally. Okay, and so from there, you can deduce the large deviation principle for the random matrices for the empirical measure of the eigenvalues and the traffic from the large deviation principle for this neighborhood distribution of graphs. And basically, for the large deviation for these graphs, there was this very nice work by Bordenave and Caputo. And then, so we considered somehow the Erdős-Rényi graphs. So from there, it was not very complicated to get the large deviation for the empirical measure of the eigenvalue of this Erdős-Rényi graph. And then it was shown that you can restrict yourself to marks which have discrete finitely many values. And the proof was not very different. And so what we had to do was somehow to be able to include all continuous possible values of the marks by kind of projective limits. Okay, I think I am my time done. Thank you very much.